All right, so now we're ready for a new topic right here. So we're still learning how to take derivative. So now let me introduce for you guys these two famous rules: product rule and quotient rule. Okay. So let me bring up a problem like this. It's only a demonstration problem to lead into the idea here to see how it's important to come up with product rule and quotient rule. But let's say you have a function f of x right here, right, and equals x squared minus 4x, right, and then there's a x squared plus 5. Right. So there's your function. Our ultimate goal is, these days it's all about, hey, you have a function and find the derivative, right? Find f prime of x or find dy dx. It's all that goal, pretty much all day long like that, right? That's what we do, and that's our job pretty much every day in class here. So yes, we want to find f prime of x. Okay. But so here's the thing. At this point, the only rule we've learned, the only rules, or maybe rules, a few rules that we've learned is one specific rule, the power rule, right? Like say you got these power terms like that, we can use the power rules, and then aside from those, we have the rule for taking derivative on the constants, we always come out 0, right? The rule for taking derivative term by term, see what I mean? Okay? So, be aware of one thing, we haven't learned specifically any rule for the case where one function being in product with another function. We haven't learned any rule like that, see what I mean? But here, let me tell you, with the limited learning that we've learned so far, we can still work on this problem. We can still handle this problem just fine. So I believe I've also taught this before, and I just want to remind you, we can always take our time foiling out, right? Even though we have a product, right? We can always take our time foiling out. See what I mean? Okay, and so foiling out, meaning before taking the derivative right here, we have to turn our function into something like this. That's the only choice, because foiling out is going to make it, all displaying how the forms are here. So x to the fourth is first term, right? And then plus 5x squared, right? And minus 4x cubed and minus a 20x. You guys agree? Right? So that's after foiling. And then we're going to combine like terms and all that and rearrange the terms. So x to the fourth is the first term, right? And then this is minus 4x cubed, okay, plus 5x squared, and please check my math if you can, okay, and then minus 20x. So these are all power terms now with some coefficient. So now we have brought our function to something that we can effectively use in the power rule and those other universal rules that we've learned by far, right? Just fine, okay? And so for the approach like this, finding the derivative isn't so bad at all. So now f prime comes out what? First term gives me, you guys are fluid with that yet? First term gives me what? 4x cubed, yes. Okay. Minus sign, what's the derivative? Next term over here. Yes, 4 times 3x squared, right? 4 times 3, you can speed up the process now. 4 times 3 making it 12, right? X squared, you guys agree? Okay, yes. And then plus, what's the next term now? The 10x, right? And the last one here is going to be a 20. That's power 1, which is right there. So we found a derivative. So we thought that it's always good like that. But let me tell you, things will become inconvenient at some point when we, because the limitation we have here is we always have to FOIL out, right? So that we can bring it down to the familiar product group. The power rules and all of that, right? But is there a more direct route like that so that we can handle directly the quotient, the products here? Because otherwise, there would be times that it takes a lot of time to FOIL things out. So we don't want to just sit there and FOIL out, right? And so the rule that we're about to learn now. All right. So the rule we're about to learn is called the product rule. This is what it says in the product rule right here. So remember, keep in mind that we want to come up with something more direct so that we can handle this problem again, but without foiling, right? And so here's how it says here. Anytime you have a function that appears to be a product of some two other functions, right? Like in our case, we got the x squared minus 4 being one little function, right? In product with the x squared plus 5, then we got our overall function being the product of some two other functions. And then we're asked to find the derivative. See, I'm starting to use that notation I've been introducing, right? We're differentiating that product in respect to x as being our main variable. So the product rule says, hey, you can find the derivative directly on a product like this, without foiling, of course, by doing this. First, you take the derivative of P. So I'm applying that differentiating symbol. I differentiate P of X, right? But then, after differentiating P of X, I'm going to simply multiply that with Q, no derivative. That's a surprise for me learning it at first, right? But then, that's not done with the product rule. We need to add, right? And so now in the next term, I'm going to keep P of X the same, no derivative. But I'm going to multiply with the derivative of our Q of X. Okay? And yes, ladies and gentlemen, that's our famous product rule again. And then this product rule right here, in the way how it looks, yes, the symbol may make it, the notations may make it look a little too lengthy. And so the shorter versions, and quite a few textbooks are using this, allow me to use the shorter and the even shorter version. So the shorter versions, many textbooks are using, you got P times Q, right? And then yes, we take the prime, meaning we take the derivative, right? So what's easy to remember here is we go, it's P prime of X times Q, no prime, right? Just like that. This is P prime, right, times Q, no prime. And we add it with, it's a requirement, it's a part of the formula. We got to add with the P of X, right? Multiply with Q prime. That's the shorter version, isn't that? Right? It does look a lot shorter, right? And then the even shorter, right? The even shorter. Okay, the short. So how about, let's call it just the short formula, right? Of course, it's shorter than the original version I wrote, but then the even shorter. And you see this thing all over Google over here. You see PQ means a P function times a Q function. You take the prime like that. You guys following? Right? And that's going to come out simply just, or as easy as just P prime Q plus P Q prime. Okay? And that's what I meant by, so we got a formal version of that formula, right? Of that product rule, and then we got the short version, right? The chopped down version a little bit, the simplified version, and we got even the shorter version like that. It's all for making it easy to remember, right? So I'm still leaving that demonstration problem here, because that demonstration problem motivated us to hunt for new rules and all that, right? But so let's now call that example 1 here. You can see how useful that can be. So let's find, how about the only function I have is f of x equals x squared minus 4x times x squared plus 5. My purpose is to restart the exact same problem there, but this time we're going to apply the brand new method we've learned. Okay. All right. So now to get into this, you can see that your only responsibility, if you're planning to use a product rule, right, the only plan you need to use is make sure you recognize properly who the P of X is and who the Q of X is. The extra notation here is just for you to understand, right? You're not required to do this in your handwritten version, okay? In your handwritten work right here, but see, think about, I put a bracket here indicating, hey, I recognize that as one function, P of X. That's just for extra clarification. The other part right here that I put that with the bracket right here, that's the Q of X, being the x squared plus 5. So the whole problem, f of X here turns out to be the product between P and Q. You guys with me that? Now in that way, to find f prime, right? To find f prime of x, that means we are getting the derivative on this product together. So let's just get straight into the rule. What we need here is a p prime of x. But how do we find p prime of x? Well, how about p is the x squared minus 4x. Right? And for now, for a lot of explanations, I'm still repeating writing that. And one day you guys should be, and that's the aim for any instructor, you guys should be making it fluent, right? So the function p right here, we take the prime, but make sure to multiply with the other function q of x without the prime. See how I'm setting it up? Okay. And it never hurts to write down the setup like that. And then now we're keeping p the same, x squared minus 4x. That's p, right? But we make that in products with x squared plus 5 with the prime. You see how I put the primes on those in certain order right there? And so now the actual work comes out quite easily. The derivative for this, now we can go term by term, right? First term gives me a 2x, second term gives me a 4. Am I speeding too fast for anyone? Okay. And then I'm multiplying with the q without prime, so x squared plus 5. Right? plus. Now, in this group right here, I got x squared minus 4x stays the same because that's p no prime, right? But now taking the prime of the x squared plus 5, it will give me 2x plus 0, right? The derivative of constants is 0. So now, ladies and gentlemen, I'm telling you that we are actually now taking the derivative. I mean, so right now the problem doesn't, because right now you see that you can still bypass using this, right? By going with that, right? I understand. What I'm showing you here is just an option, another option right here. And then trust me, when we get into the later kind of functions right here, then we are sort of like more forced into doing this route right here. Because that's the only way. So right now, yes, you got more than one way to handle the problem, right? You can FOIL, and then get your derivative. And then here, a more direct route, you can just apply the product rule. And then at some other problems that become more challenging, then the product rule really is your only option with that. Right? So that's why we're learning as many tools and techniques as possible as we can. Okay. And so just be patient on that, and you see the reason why you have to know this. But anyway, what I want you guys to see is the two answers at first look a little different, right? You see, if we were using the foiling, we come up with something like this, and then using the product rule, we came up with something like that. But you take your time foiling out each one of these groups right here. 2x minus 4 times x squared plus 5. Take your time foiling. What do we get for this? So this is just optional to really to show you the results will come out to be the same. The 2x times x squared giving me a 2x cubed, right? And the 2x times 5, they're looking at a 10x minus 4x squared, right? And minus a 20x squared. I mean, the 20, not 20x squared, just 20, right? And then we add it. So here we got 2x cubed, right? And minus 8x. You guys read that? And then we combine like terms. The 2x cubed and the 2x cubed here combined together is going to make it 4.
It's minus 8x squared on here.
What's that? You were right.
Squared.
Yeah, that very last term. Yeah. See, I still make those silly things all over. And then, so we got 4x cubed here, and then the minus 4x squared with the minus 8x squared, yes, it's making it a 12x squared, right? And then there's the 10x right here, plus 10x. The last term is minus 20. It agrees exactly with the other result. Okay? And so yes, as of right now, when you learn this rule, you still question, you still concerned a lot about why we have to learn that, because we already have a way of handling this. But be patient on that. Right? It will come to that point where you running into a function where the product rule is the only way. You know what I'm saying? I mean, let me remind you guys haven't seen how to take the derivative on trig functions yet, right? And on exponential functions, right? And what about when exponential functions multiply together with a trig function? It's all product together. How are we going to find the derivative? That's why we need the product rule for that. Okay. So got one example done with showing you how to use the product rule. Okay. So let's look at another problem here to get into the idea, motivate into the idea. So we got y equals x to the fourth minus 3x squared over x cubed. So that's our function. If we want to find 1x. This is simple indicating that I want the derivative of this function. So we've got our function written in the equation format together. So this problem can be done using the technique we have learned from before. So I'm talking about before we even have to learn about the quotient rule. And what caught my attention here is that what we have here is a quotient, right? But then we don't. Before we learn about the quotient rule, we can see that the function here, algebraically, we can turn that into, so the x to the fourth minus 3x squared over x cubed, right? And I have to remind you again, think about before we learn the quotient rule, we only know the product rule. I mean, we only know the product rule, the power rules, right? Those universal rules. Obviously here it's not a product, right? So we can't use the product rule, so the power rule may work, right? And then those universal rules are working with term by term and finding coefficient and all that. So now, algebraically, I can break that down into x to the fourth over x cubed, right? Because the two terms in my numerator. And then we're subtracting the 3x squared over x cubed. And So that means I can reduce my function here to a final expression. It's x to the fourth cancel with x cubed, it will be just one single x to the first power. And here we're subtracting, now x squared is canceled away with x cubed right here, giving it 3 over x. You guys all follow me on that. Yeah? But that means further we can rewrite that as, well, the first term is clearly in the power form of a function, right, of the x here. Here we can rewrite it as a 3 times x to the negative 1. So we can make that x minus 3 times x to the negative 1. So now we can, with this here, we got 2 terms, right? So universal rule that we can say, hey, we can find the derivative term by term. And then each one of the terms here is a power, so we can apply the power rule on each of the terms here. So I'm not saying that we can't do this problem, right? We still can. So the derivative here, dy dx, is going to be, right, first term here gives me 1, right? The second term here gives me minus 3 times the negative 1 multiplied down, right? And then x here to the negative 1 minus 1. And then that's all together going to give me 1, minus 3 times negative 1 is a plus 3, x to the minus 2 power. So we found that we can find the derivatives just quite easily. Okay? And then that's, in case we're asked to write the final derivative without a negative power, right? Then we can write it as a 1 plus, and there's a 3 over x squared. You guys follow it? So, yes, I'm not saying that we can't find the derivative for this function without any new rule to learn here. But the way we've done here, the way doing that here, we definitely have to bring in a lot of algebra, an intensive amount of algebra here in order to bring it down and then bring that into the familiar rules that we can use. So is there a way to do things differently? Like say what we have here is a quotient, right? On top here I have some kind of p of x polynomial, and we can quotient with a q of x here, right? So we that form a polynomial over a polynomial. So is there a way that we can work with the quotient here directly, a rule to find the derivative that we can work with directly? Okay. And so that brings us into the idea of the quotient rule was invented. See, it's the way how it was. Think about if you were one of those earlier generation mathematicians right there, you work through the power rules enough and you use the algebra to chop it down into terms, and then you keep getting tired of doing that. So that's why you need a big motivation for inventing a new rule like that. So the quotient rule says when we're taking the derivative of a quotient, some function p of x over some function q of x, doesn't have to be rational function as long as you have a quotient, right? So taking the derivative of something like this, okay, in respect to x as our main variable, then the quotient rule is stating that the way we can do that, we can find the derivative, right, for p of x in respect to x, right? And then we multiply that with q of x without derivative. And then we're going to subtract. So as we learn through this quotient rule here, make a close connection with the product rule we learned earlier. So the product rule, when we learn the product rule, it's about the first function, taking the derivative of the first function and multiply with the second function without derivative, right? So it has some similarity right here. But then when it comes to the product rule, it was supposedly a plus here, but now doing the quotient, we do a subtraction. The corresponding sign like that, the division goes correspondingly into a subtraction. And so now we're subtracting p of x and multiply with the derivative of q of x. And then it stays in that order that, since p is on top, so we take the derivative of p first, right, and multiply with q without prime, and then we put that before the subtraction right here, and then we subtract p with no prime in products with the derivative of q. But then that difference here is not enough. We need to divide. So that's part of the quotient rule here. We need to divide by q of x squared here. Okay? The function in the denominator here, we need to square that, put that in the denominator of our derivative, and that completes our quotient rule. Okay, so this is the big formal form right here. Okay? And then it gets a little shorter for convenience. We got, let's say I think about p of x over q of x, right? And our attempt here is to find the derivative, take the prime of that. Then the short form the short revised version is, see, e prime of x multiplied with q, and then we subtract, and see, once again, in that order, p of x, in that original quotient, it stays on top first, right? So we take the derivative of p first, multiply with q, no prime, then we subtract. And now I'm going to keep p the same, and I'm going to multiply with q prime of x. And then here, in the denominator, we divide by q squared of x. So that's, some form that's a little bit shorter, right? So there's a short form of that, the quotient rule right there. And there's even the shorter form, most convenient one that you see throughout so many textbooks. There's a short form, and then there's even a shorter. And so, a short p over q, right? Taking the derivative, which is easy enough as p prime q minus p q prime and divided by q squared. Right? And by q right away. So there's a short form of our quotient rule, and then there's even the shorter form, which so many textbooks summarize that into. So now let's see how the derivative, that quotient rule is going into becoming useful for us. I still want to retain the work for that, that problem that's motivated into the idea here. So with this demonstration problem, we got that quotient and then the derivative that we have found previously, being 1 plus 3 over x squared. Right? And so the work here that I already erased. Let's now call that example 2. Okay. Go ahead and write down the instructional problem. All right, so for this problem right here, I purposely brought in the exact same problem that we did in that demonstration problem right here. So throughout the demonstration problem, we found a derivative, but the way we found that, right, the way we approached that was completely different. We used the algebra to break it down, and we didn't do anything directly with the quotient. So we turned the quotient algebraically into multiple terms, right? And then each term we re-express that as a power so that we can apply the power rule. But now, how about this? The exact same function. I'm seeing that here as a quotient, right? So this time I'm seeing it clear. Let me make that clear up here. This numerator part right here, yes, you can think of that as your p of x, right? Some function doesn't have to be polynomial. That's down here. We can see that as some function q of x, right? So now we have a quotient between p and q right there. And then the order says, and the order is showing that p is on top in the numerator, right? And then q is at the bottom and in the denominator. And so in that way over here, let's apply this time same function, but let's apply the quotient rule to find the derivative. So dy dx, you can just get straight into the derivative right here without beating around the bush with the algebra. So it says p prime of x. So I'm going to have x to the fourth minus 3x squared, but we take the prime of that, right? And we multiply with the function from the denominator without the prime. You guys follow that, okay? Right. So I'm just setting up the formula with the proper components, right? Put in and then subtract according to the quotient rule. And then now I'm going to leave it x to the fourth minus 3x squared, no prime, right? But that's going to need to multiply with x cubed prime, or the prime of x cubed. And then we're going to divide it by the square of the denominator, q squared. Right? So q squared, so x cubed all squared. Those things in the denominator. So that's just a setting up like that. But now when we get into doing it, my board here is still a little busy for that, but it's okay. We continue that small space here. So in that numerator, x to the fourth minus 3x squared, when we take the prime here, it gives me 4x cubed prime minus 6x. Okay, you guys agree? Right. And then that needs to multiply with x cubed. And then I'm subtracting, right? And then there's your p of x that we keep the same. X to the fourth minus 3x squared, right? But then the derivative of the x cubed, I'm going to make that as a 3x squared, another 3x squared. Okay? And we put that over the x cubed squared. So x cubed squared all together is an x to the 6th power. Because see, it's x cubed, and we raise that to another power, so that means in the rule of algebra, right? We multiply these two powers, making it the final power being the 6. And so at this point, technically we found the answer, but it just, of course, no instructor is going to be happy seeing a final answer like that, right? So we are advanced enough in math that we know how to do some certain amount of simplification. So now the next step here is just to simplify down the answers a little bit. So, but before we can simplify, let's go ahead and distribute these terms again, right? So distributing the x cubed for the two terms there, it's giving me 4x to the 6, right? Minus 6x to the 4th. You guys agree? And then I'm subtracting it, so every single terms here are gonna switch signs, and then every single term here is gonna switch sign, but we can multiply with the 3x squared as well. So the 3x squared multiplying will switch sign, we're making it minus, right? 3x to the 5th. You guys following? Okay. And then we add it, right? 3x squared multiplied with 3x squared, but at the same time we switch sign, that's why it became a minus with that. So we got 3x to the 4th. Okay. And then all of that is over x to the 6th. Okay. Okay. Yes?
Why is it 3x?
Got to the 6th. Okay. Yes. Thank you for that correction. So now we're gonna keep simplifying it further. So again, I gotta make it clear, we already got it done to the derivative at that step right here. But then the later one is just to keep simplifying it down. So now I'm looking at combining the like terms of these, right? That's making it 9x to the 4th. Correct that for me. Okay. Okay. So now the 4x to the 6, 3x to the 6, subtracting those out, or combining like terms, right? That's giving it x to the 6. Okay, only one for that. Okay, the minus x to the 4th, and combined together with the minus 6x to the 4th, combining with the 9x to the 4th, which is making it 3x to the 4th. And then we're putting that over x to the 6th. Okay. And then we can further simplify. So you can technically stop right here, but then usually we want to simplify to the most reduced form, right? So simplifying it down even further, we're looking at it's going to reduce down to the x squared, right? Plus 3x here divided by x squared plus 3. And that's how we turn it into the most reduced form. Because we had a common factor of x to the 4th here, right? So I factor that out, right? And I cancel away with the x to the 6 in the denominator. So we came to that. So now the two answers we're looking at, the earlier method that before we had to use with the method that without using the quotient rule, if we came to 1 plus 3 over x squared, right? See, think about adding these two terms right here and making that into one fraction. And yes, we're looking at x squared plus 3 over x squared. And that's how the two answers agree, right? The answer using the work without the quotient rule and the answer using the quotient rule like that, right? They all turn out the same way like that. See what I'm saying? No? And of course, right now I'm just illustrating for you the idea that we got the quotient rule invented, right? And it works, and it gets you the derivative anytime. Right now, it's not too convincing of why we have to learn it, right? But later on, we're going to get to some other function that we will be better convinced that it's better to use the quotient rule like that. Okay. So it's pretty straightforward with using the quotient rule.